Welcome to this mix looking at Newton's laws, and this is a revision of work done at National 5 and continuing in the R dynamic unit, first unit. So what we're looking at, the three laws of motion, how to define the unit of force, the Newton, and how to solve some second law problems. So Newton's first law, object will remain at rest or travel in a constant velocity in a straight line unless acted on by an unbalanced force. Newton's second law talks about when there's an unbalanced force that an object will accelerate, also described as F equals ma. The Newton is defined from Newton's second law, and 1 Newton is defined as the force required to accelerate a mass of 1 kilogram by 1 meters per second squared. So this is coming from your F equals ma, and it's saying if I have 1 kilogram and I accelerate it at 1 meters per second squared, that will require a force of 1 Newton. For Newton's third law, it's described as for every action there is an equal but opposite reaction. Sometimes it's also described as A exerts a force on B and B exerts an equal and opposite force on A. Either of those is perfectly acceptable. So we'll already know that force is a vector, so it has magnitude and direction. If we have vector quantities, we can add them up to find the resultant. Those could be at 90 degrees, tip to tail, or they could be at different angles to find our resultant. We also know that if we've got a force at an angle, we can split it into its two components, the horizontal and the vertical force, just like we can do the same for a velocity at an angle in a projectile. Quick word about free body diagrams. A free body diagram is just a diagram that shows the forces that are acting on an object, and it helps us see more clearly so we can then draw a vector diagram if we need to. We make everything as simple as possible, and so our free body diagram is usually just a box. The kind of names of forces that we might use, the weight for the downwards force due to gravity. Don't use gravity, you need to make sure you put the force due to gravity if you're going to use that label. Tension, which might be in a string or a cable pulling something. Friction, the force that opposes motion. Thrust or engine force, the force due to an engine or pedaling on a bike. And reaction force, the force of the ground on the object in reaction to the force of the weight on the ground, as in Newton's third law. So remind ourselves about balanced forces. Balanced forces are equal and opposite forces. So is that balanced? Yes. Is that balanced? No. The force on the right is less than the force on the left, so that is the same as an unbalanced force of 5 newtons to the right. Is that balanced? No. So that is the same as the unbalanced force of 12 newtons. Not 12 newtons, 2 newtons to the right. Is this one balanced? Yes. Okay, let's look at some problems using F equals ma. So we draw a free body diagram to indicate all the forces, and we put the direction of the unbalanced force on our diagram to show us the direction of the acceleration, and use Newton's second law, F equals ma. So here's a free body diagram for a car pulling a trailer. So rather than drawing the car, we just draw a box for the car. So downwards, let's start on the vertical forces. Downwards we've got the weight, which we might have to work out, m times g. Upwards we've got the reaction force, So remember from Newton's third law, the force of the car on the ground is the action, the reaction, the force of the ground on the car. Forwards, we've got the engine force on the left. Backwards, we've got the friction force. This car's pulling a trailer, so we also have the tension force as well. Man pushing a shopping trolley of mass 20 kilograms with a force of 40 newtons. If the friction is 10 newtons, calculate the acceleration. Remember Newton's second law, F equals ma. F is the unbalanced force, so work out the unbalanced force, substitute to get our answer. Okay, here's somebody pulling a roller, coming to roll their cricket pitch or their lawn, and we've got information about the roller. So the person's pulling this at an angle, and so straight away we need to know what the acceleration is, but we need to know the force that's horizontal. What is the components of the force that's there? And this is done in the same way as we do our work for resolving projectile velocities. But the one we're interested in is the horizontal one. So we're only going to use F cos theta. We're not going to bother with the vertical force. So we work out the force, F cos theta, and we use that with the mass and our free body diagram to work out the acceleration. So we've got friction on the other side, so we can work out the unbalanced force and then the acceleration. Okay, now you should try some of these problems for yourself. So you should be able to apply Newton's second law, and you should be able to resolve forces at an angle.